Okay, lesson 115, limits at infinity and horizontal asymptotes. So when we're looking at horizontal asymptotes, we're basically looking what does the y value approach as the x value approaches negative infinity and positive infinity. Does it approach a specific number, or is it growing without bounds? So our rules for the horizontal asymptotes has to deal with the degree of the numerator and degree of the denominator. So you really just want to look at the degrees here. Let's see, so if our denominator, oh wait, I need a pencil. Here we go, denominator grows faster, like you have not as big number on the top over a super duper big number on the bottom, then your asymptote was going to be y equals 0. If the numerator and denominator grow equally fast, then you have a big number over a big number, which is basically 1. Well, actually, no, since we're talking about limits, let's just put it as limit notation here. Okay, we'll erase this. All right, this would be like approaching a number, like 1. It may not be 1. Okay, if the numerator grows faster than the denominator, then you've got the bigger number on top. So this is going to approach infinity. The things you need to do, remember those for the horizontal asymptotes, is I just like to think of it as, instead of how do you know which one's bigger, look at the degree of each, the numerator and denominator. And that'll help you figure it out. Oops. There we go. Numerator versus denominator. Because if it's a proper fraction, like this one, okay, where the top is smaller than the bottom, then your horizontal asymptote is y equals 0. If your degrees are the same, then you're going to have y equal to the leading coefficients, basically, the numerator or denominator. And then if you have one that's an improper fraction, where the top is bigger degree than the bottom, then there is no horizontal asymptote. There is a slant asymptote instead. All right, so first let's recognize which functions grow faster as x values get larger and larger. So when we look at these, okay, so here's our different functions that they give us right here. We want to know which one grows faster. Okay, so they gave us a chart. They gave us a few x values, and they got larger and larger, like this one's already to 1,000, that's 100, that's 10, that's 1. So you can kind of get an idea of which one is which here. But when you're looking at the order, the one that is the biggest, looking at this first column, is right here, right? That's the largest one. So this one grows the fastest. Okay, anything that's exponential, they grow the fastest. Okay, so then the next fastest would be this one, which is e to the x. Then you'd have, say, 2 to the x. Now, notice these are all very similar. So we need to look at the ones in the other columns, because see, we have like 1, 2, 3 here, but see all these have the same one. But let's look at this column to see which one would be bigger. So this one grows faster, x to the 10th. Then it would be x to the 3rd, and then it would be x squared. And then, of course, the last one would be this logarithm function, natural log. So you need to recognize which functions grow faster. Okay, so on this next part, find the horizontal asymptotes. So on the horizontal asymptotes, remember we're looking at degree. So here I'm looking at the degree of the top versus the degree of the bottom. So notice that the degree on top is larger than the degree on the bottom. So there is no vertical asymptote here. I'm sorry, horizontal asymptote. On the next one, the degree on the top and the bottom are the same. So that would be y equal to the leading coefficients. So that would be y equal 1/3. when I look at the next one here, this is x squared. So that is a proper fraction because it's smaller on top. So this would be y equals 0. Let's see, this next one we have x times x, so that's x squared. And this would be x squared also. So since those are the same, it'd be leading coefficients. So this would be just a 1x squared on top here. This would be a 16x squared. So our leading coefficients would be 1 over 16. Notice how I'm not really worried about anything else on there, just the leading coefficients. All right, so what if we have something with a square root? Well, this square root of 2x squared would give us, that would be like the absolute value of 2x. And then on the bottom I've got 3x. Well, notice that is the same. So what we need to be concerned with is that this could be positive or negative inside here. So we end up having 2/3 and negative 2/3 on this one. Okay, so this one actually has 2. Because remember, when you take the square root, you got to worry about the signs there. All right, so let's check. On this one, let's see, that one and that one, this is going to give me the absolute value of 2x squared over 3x squared. Since it's squared, though, on inside, it's always going to be positive. So that's y equal 2/3. So notice the difference here. Okay, let me write that. Squared means it's always positive. All right, so number 10, evaluate this limit. Oh, wow. Let's see, as x approaches infinity. So this would be like -4 e to the 1 over a very large number. Well, that means this 1 divided by a very large number is getting closer and closer to 0. And we know e to the 0 is 1, so this is -4 times 1, so this is just -4. Ooh, that's kind of tricky. All right, so the next one, this would be 5 over e to the x power, because it's a negative, so I need to do the reciprocal, right? Negative exponent, so it goes to the bottom. And if I plug in an infinity, e to the biggest number, this would be like 1 over e to the big number. So that would be approaching 0, wouldn't it? 5. No, wait, let me write it like this. I think it'd be better if I write it like this. Sorry about that, guys. This doesn't erase the same as that other program. Okay, so 5 times 1 over e to the x, which is 5 times 1 over e to the infinity, which is 5 times getting to be closer to 0. So that's going to be 0. Yeah, that looks better to me. Okay, great. Okay, we got a few more questions on this part. Looking at the trig functions, horizontal asymptotes. Now, this one, I want to point out, is different, okay, than what we're used to. Because remember the other one we had, it said the limit as x approaches 0 of sine x over... Actually, you know what? Let me write that down. I'm going to put it up here. The limit as x approaches 0 of sine x over x was equal to 1. But notice how that's different, because this one has x approaches negative infinity. Okay, so this is a different one. So I just wanted to point out the difference there. So just pay attention to that. So on this, as sine approaches a negative infinity, well, I know this top approaches is always going to be between -1 and 1. The bottom one is going to be like a very large negative number. So this one bounces back and forth, so it's actually going to approach 0. So that was a little bit more confusing, because remember, if you have a horizontal asymptote, you can cross the horizontal asymptote. In between is bouncing back and forth between -1 and 1. Right in the middle of that is 0. Bottom is just going to be a larger negative number. Okay, so on number 13, the limit as x approaches infinity of -3 times cosine of 1 over x, so that'd be -3 times cosine of 0, because 1 over infinity, 1 over a big number, is getting closer and closer to 0. So this would be -3 times 1, which is -3. Okay, on the next one, the limit as x approaches infinity of sine x. This one actually does not exist. Okay, that limit does not exist because it's oscillating. Oh, that looks terrible. Okay, between -1 and 1. So the next one, this would be 5x. Oh, you know what? It's going to be the same thing. This is going to be does not exist because of that part right there. It's doing the same thing. It's oscillating between -1 and 1. All right, so the rest is for you to work. I will post those answers so you can check your work and then let me know if you've got questions.